Okay, so let's imagine this scene together.
Yeah.
It's the year 499. The place is Kusumapura, ancient India.
Yeah.
And something big is happening in the sky. A lunar eclipse.
Yeah.
Now, back then, most people wouldn't have just seen this as some cool event. You know, it would have been terrifying.
Oh, yeah, absolutely.
They'd look up and see the moon disappearing. And
like something's eating it.
yeah, I think some monster is devouring it. And right in the middle of all this fear and superstition, there's this one guy, Aryabhata.
Mm-hmm.
And he's totally calm. He knows exactly what's going on. And here's the thing. He figured it all out from something really simple, just watching the shadow of a stick in the ground.
I mean, that image right there is just so powerful, right? Yeah. This total panic, the myths people believed, and then you have Aryabhata just calm, collected, using math to figure out the cosmos.
Totally. So in this deep dive, we're going to see how he did it, how Aryabhata took these everyday things, shadows, combined them with geometry, and just changed how we see the world, the whole world and space.
And what's really interesting is we have these writings from Aryabhata himself, like these verses, especially numbers 14 to 18. They're like little clues to how he took measurement, how he built up this like incredible understanding of astronomy.
And it's a really good example for everyone listening of how just paying attention and thinking things through logically can lead to huge discoveries. We're going to see how even a simple shadow has all these hidden depths. And hopefully you'll have a few aha moments with us along the way.
Yeah, and I think it's really important to remember the context too. Back then, people explained things with myths and gods, right? Yeah. Aryabhata comes along, totally different. He's all about math, about observing nature. That was a big shift towards science.
For sure. Okay, so let's get started with our first part. We're calling it the cosmic calculator, the Gnomon and right triangles. Aryabhata used this thing called a śaṅku. That's S-H-A-N-K-U. It's just a vertical rod, basically a stick. But watching its shadow turned it into his cosmic calculator.
Right. You know, the gnomon is so simple but so direct. It links the sun's position to a length you can measure right there on the ground. And by watching that shadow, how long it is, which way it points over a day, over seasons, Aryabhata could figure out how the sun moves, even where he was on Earth, like a really, really accurate sundial.
Exactly. Now this brings us to verse 14. The original Sanskrit is Sakopramachwaga chavarga sayuta katotasya padayotat syat viguchakorfakorifaptamio 14. And the first part, the most important for us right now, translates to having added the square of the gnomon's height to the square of the shadow, take its square root.
Okay, so this is where it gets cool, because what he's talking about is the Pythagorean theorem. You know, a squared plus b squared equals c squared.
Right.
So picture it. The gnomon standing up, that's one side of a right triangle. Okay. The shadow on the ground, that's the other side.
The base of the triangle.
Exactly. And then you draw a line from the top of the gnomon to the tip of the shadow. That line is the hypotenuse, the longest side.
So Aryabhata saw the shadow as part of a right triangle. This triangle connects the earth and the sky, and that hypotenuse, that's the sun's ray, and the formula is that hypotenuse equals the square root of the gnomon's height squared plus the shadow's length squared. We can write it as hypotenuse equals the square root of g squared plus s squared, where g is the height of the gnomon and s is the shadow's length.
And you know, the really amazing thing is, our source points out that Aryabhata is talking about the Pythagorean theorem like 1,000 years before it shows up formally in Europe. Way ahead of his time.
Yeah, totally mind-blowing.
Yeah, makes you think.
And it wasn't just some theoretical idea either. Farmers back then actually used this. They'd tie knots and ropes to make 3, 4, 5 triangles.
Because those triangles always have a right angle.
Exactly. They used them to make sure their fields had perfect right angles. Super practical.
So smart, right? Like you have this advanced math being used for everyday stuff.
Yeah, a really cool connection. Now let's look at the second part of verse 14. Divigajeker befuktamio. The source mentions it's a bit unclear exactly what this means. Scholars have different ideas. But it seems like Aryabhata might be looking at the connection between the hypotenuse, the gnomon's height, and maybe even early trigonometry. Maybe figuring out something like the sine of the sun's angle.
That's right. We might not know exactly what that line means, but it shows he was definitely thinking about the relationships between the sides and angles of these triangles. And that's like a first step towards trigonometry and more advanced stuff later.
Okay, so we've seen how Aryabhata used a stick and its shadow to understand the sun's position. Now let's move on to our second part. Beyond the sun, finite light and city planning. Here we switch from the sun, which is super far away, to a closer light source, like a lamp,
See, this is where it gets really interesting, because Aryabhata realized that shadows work differently depending on how far the light is. The sun's so far away, its rays are basically parallel. But a lamp that's close by, the light rays spread out more, and that changes the shadow's shape and size. Got it. And verse 15 gives us the formula for this closer light situation. The Sanskrit is Shukugucha Shokuvijavivara Shokuvijavivara Dam Yalabha Sachai Vie Shokumilanhai 15. In English, that's the gnomon's height multiplied by the distance between the gnomon and the base of the light source, divided by the difference between the light source's height and the gnomon's height, is known as the shadow, measured from the gnomon's base.
Okay, so let's break that down into something we can picture. The shadow length, let's call it S, is equal to the height of the gnomon, which is G, times the distance between the gnomon and the light source, that's D, all divided by the light source's height, which we'll call L, minus the gnomon's height, G. It looks like this: S, G, E, D, L, G. And our source gives a really helpful example. Let's say you have a 1 meter rod. That's our gnomon, so G equals 1 meter. Then there's a lamppost that's 5 meters high. That means L equals 5 meters. And let's say the distance between them is 8 meters. So D equals 8 meters. We put all that into our formula. Shadow length, S, equals 1 meter times 8 meters divided by 5 meters minus 1 meter. That's 8 divided by 4, which gives us a shadow length of 2 meters.
You see, it gives you an actual measurement. And this shows how Aryabhata understood similar triangles. You have one big triangle made by the lamppost and its imaginary shadow,
Right.
and another smaller one made by the gnomon and its shadow.
Okay. And here's what I think is so cool. Aryabhata didn't just do this for fun. The source mentions that architects and city planners could have used this. They could design cities to make sure enough sunlight reached houses and other buildings.
Think about that. No fancy tools, no computers, just this math. It was important. Sunlight wasn't just nice to have. It was crucial for people's health.
Definitely. And the source also says surveyors could use this. They could even measure the width of, like, a river that's impossible to cross just by taking shadow measurements from one side. They could figure out the distance to the other side. It's amazing how this simple math helped solve real-world problems back then. So from understanding space to building a city, shadows and triangles were super useful.
Absolutely. It really shows how they connected those big ideas to everyday life. And that's a classic thing in ancient Indian math and astronomy. It's not just theory, it's about using that knowledge to make people's lives better.
Okay, so we've seen how Aryabhata could use one shadow measurement to figure things out. Now let's step it up. Our third part is reaching the unreachable measuring distances. This is where we see how clever he was using multiple shadows to find distances that you wouldn't be able to measure directly.
Right. Here he takes that basic idea further, and he's essentially doing triangulation, but not with angles like we do today. He's using those changing shadow lengths as his data.
Exactly. Verse 16 gives us a peek into this method. The Sanskrit is Chaigweta Chayagravivarmunena Bajita Kuishakuweta Yosavinia Vumirpetin 16. The source explains it as a way to find horizontal distances or heights using two shadow measurements from different spots.
Okay, so let's picture this. You have your gnomon. You measure its shadow at one point. We'll call it point A.
Got it.
Then you move the gnomon a known distance, like you take a certain number of steps, we'll call that day, to a new spot, point B. You measure the shadow again. Now you have two shadow lengths, and you know how far you move the gnomon. With that, and using similar triangles, you can calculate the distance to something far away, like a tree or a building.
Like a classic surveying trick. The source even jokes you could use it to measure the distance to a spy.
Yeah.
You have your two shadows, you know how far you moved, then you use ratios based on the similar triangles, the small ones from the gnomon and the big one, to that distant object to figure out the distance. Pretty neat, huh?
Really neat. It's all about similar triangles. As you move, the shadow changes length, and that tells you how far that object really is.
And get this, the source says Aryabhata could use this for astronomy too.
Oh, yeah.
He'd watch how the gnomon's shadow changed at noon throughout the year. By doing that, he could track the sun's path and even predict the solstices, the longest and shortest days, within a few hours. Pretty precise for back then.
Really precise. By measuring the shortest noon shadow in summer, the longest in winter, and knowing the geometry, he could figure out exactly when the sun reached its highest and lowest points in the sky. And that was key for calendars and understanding the seasons.
And it gets even better. The source mentions that much later, the scholar Al-Biruni used a similar technique to estimate the Earth's circumference. He added angle measurements too.
Oh.
But it started with the same idea, a stick and its shadow. So you can see how this basic method influenced science for centuries.
Yeah, inspiring people to ask even bigger questions. It shows how those early discoveries can really change things.
Okay, so we've seen how Aryabhata used shadows to measure things on Earth and track the sun. Now for the final part, Act 4, decoding the darkness, the geometry of eclipses. This is where his knowledge really shines, especially when you think about how scary eclipses were back in 499 CE.
Oh, yeah. Imagine, right? A lunar eclipse back then. It wasn't just something cool to see. It was terrifying. People didn't know what was happening.
Right, they'd think it was a bad sign, or the gods were angry, or something awful was going to happen. The source says markets would crash, armies would even mutiny, and kings would make sacrifices to try and appease the gods. It was a big deal. But Aryabhata was different. He had this math knowledge, so he could predict when the eclipse would happen and how much of the moon would be covered. He'd basically be like, don't worry, the shadow will be at its biggest at this time, then it'll go away. It's all good.
That's amazing. Like, totally changing how people saw this event.
And he could do that because of what he lays out in verse 18. It's the key to his eclipse explanation.
Okay, so verse 18 of the Aryabhatiya, it goes, Grosone deva drovrosa di gosagui bachete travena grasone yogolabho zapata sharaparasparatho. 18. And instead of translating it word for word, which can get confusing, the source gives us a simplified version. It talks about two circles that intersect, and then calculating what are called the arrows in Sanskrit, short of the segments made by the overlap. That overlap area is the grasa, the eclipse magnitude.
So he's basically thinking of a lunar eclipse as two circles overlapping. One circle, let's call it circle A, is the moon. The other, circle B, is the Earth's shadow. And when the moon moves into that shadow, boom, you have an eclipse.
And those terms, grasa and shadow, they're important. Grasa is how much of the moon is covered by the shadow, like how much of it is, seemingly eaten away.
Right.
And shadow measures how deep that shadow goes into the moon, like the depth of the bite.
So Aryabhata was figuring out exactly how these two circles, the moon and Earth's shadow, would overlap using geometry. And he was doing this with math at a time when most people were freaking out and blaming everything on the supernatural. Pretty incredible, right?
Yeah, totally. And the source makes a great point. It says, this is basically the first example of computational astronomy. Aryabhata wasn't using myths or gods to explain eclipses. He was using geometry, using math.
And here's something that just blows my mind. The source compares Aryabhata's calculations for how the eclipse changes over time, those shadow curve derivatives, to calculus.
No way.
Yeah, and calculus wasn't developed for another 1,500 years by people like Newton and Leibniz.
That's amazing. He didn't have the same tools or language, but he was thinking about how shapes and their overlap changed over time. That's like a super early version of calculus.
Right. So the point is, Aryabhata used geometry to predict when eclipses would happen and how much of the moon would be covered. He gave a scientific reason for something that had been a total mystery for so long, and that's a big step in how we understand the universe.
Yeah, he moved us away from those myths and towards real understanding. His work was crucial for everything that came after in astronomy.
Okay, so we've seen how Aryabhata used shadows and triangles to measure, to track the sun, and even to figure out eclipses. It's pretty impressive what he could do just by observing and using some basic geometry.
It really shows how powerful those basic principles are. Even something as simple as a shadow can tell us so much about the universe if we know how to look at it.
And think about it. Today, we can just check our phones to see exactly when and how big an eclipse will be. But that's all thanks to people like Aryabhata who weren't afraid to think differently and to use math and logic to explain the world.
That's such a good point. Like, we went from being scared of eclipses to understanding them, from superstition to science.
And this brings up a question for you listening. What other simple, everyday things might have hidden secrets just waiting to be discovered? Aryabhata's story shows us that there's always more to learn, more to understand if we just pay attention and think things through.
Yeah, like he really shows that drive to figure out how the universe works. Really inspiring.
And speaking of figuring things out, in our next deep dive, we'll keep exploring Aryabhata's work. We'll look at how he actually measured the Earth's circumference using a well and the sun. It's a really cool story, so make sure you don't miss it.
Can't wait for that one. It's amazing how we took those same ideas and scaled them up to tackle a huge question the size of our planet.
All right, that wraps up our deep dive for today. Thanks for joining us on this journey through the mind of Aryabhata.
Yeah, thanks for listening.
And until next time, keep looking closely at those shadows. You never know what secrets they might reveal.
Exactly. You never know.